Hello, my name is Claire,
My name's Shelley.
My name is Mohammed.
My name is Christian.
and this is our final review video. So let's start with lecture one.
So for lecture one, I'm just gonna go to the actual content here. So basically it kind of introduces us to what static and dynamics is. So wait, I'm sorry. All right. So right now we have like a definition of statics, which is basically concerning like in equilibrium things that doesn't move yeah, basically statics problem, and we have dynamics which covers kinematics, covers velocity, acceleration, and everything. So we have those two that we're gonna cover in this class. So and then another thing that we have is like a particle and rigid body. Particle is basically we are taking something like to a point of mass. So the shape of the particle or like the object doesn't matter because we're taking it as a particle. Whereas rigid body, you actually have to look into the actual shape and consider all the forces where the forces acts. And yeah, I think that's about it for like lecture one. And we also go to like Newton first law, second law, and third law. But these are all like quite simple, and I'm sure like
And they'll be discussed later
yeah,
more in detail.
yeah.
So lecture two. Oh,
So going to Claire, she's gonna explain
or no,
lecture
it's
two.
Christian.
Oh, Christian, sorry.
Yeah. Do you want this thing? Can you share it for me?
Oh,
Do you need
yeah.
to write it?
Yeah, I need to write it.
Thanks. We're gonna be sharing screen now.
You can see.
One second. Oh, there we go. There we go. Okay, perfect.
So for lecture two, we discuss about 2D particles, specifically force equilibrium. But before that, we need to understand vectors and many of the common laws that we see throughout the whole course. One of them being the um, uh,
Um,
one of them being like the triangle law, which is about having two vectors going in a certain direction and knowing how to combine them to find the resultant vector. So in this case, the resultant vector would be here, of F1, F2, and then F of the resultant. And the way to find that would be doing the tip to tail method of F1 to F2, the tip of F1 to the tail of F2, and then the resultant would be the vector that goes that creates the half of the parallelogram. Another important law would be um, law of cosines, which is about having a triangle of ACB, and then its lowercase values, and then it would be the formula is c squared a squared is equal to a squared plus b squared minus 2ab cosine of c. But this is just a general formula that we follow along. It's all dependent based on the angle inside that we need to find specifically. Another one we cover is law of sines, which is basically from this previous triangle of just how everything is just the sine of A over A is equal to sine of B over capital B, and then so on and so forth. So after that, we can finally get to 2D particles. A good way to yeah, a good way to do this would be something that we take over this whole course is force equilibrium, which is the state that um, the right-hand side is either staying perfectly still or it's in constant accelerate or no acceleration, so just constant velocity. So it'd be F is now equal to 0. And in this case, because this lecture covered particles, we don't have to worry about a rigid body. We can just view objects as one whole point that holds all the forces that we're asking for. So for example, let's say we had a box strung up to two strings. The rigid body for that would be a particle starting here and then.
Free body diagram. No, you said rigid body.
Oh, sorry,
Yeah, free
thank
body
you.
diagram.
The free body diagram would be the particle of the box, and then the first ones would be weight of the box, and then the tensions along the strings. And that about sums it up for 2D particles. To find the certain tensions would be to just do it in the X and Y direction based on the FBD that you drew out, and then you can solve for the missing variables after that.
Christine, can you explain real quickly like the difference between like scalar and vector?
Yeah, of course. So scalar is something that has a full magnitude, and then a vector would have a direction. So for example, let's say a vector would be like a hat. It would have the components of like I hat. In this case, for a 2D particle, I hat and J hat specifically only because there is no 3D component to it. And then while let's say we wanted the magnitude version or the scalar version of A, we would have to find it by squaring and square rooting its components in order to find its full magnitude. So the main difference is that vectors have direction while scalars are just purely just the quantity.
All right.
Okay. What's an example of a vector?
Force is an example of a vector.
So like weight.
Yes, it would be.
Cool.
Yeah. And I guess an example of a scalar would be like speed, right?
Yep.
Yeah.
Nice. Okay.
Thank you.
Okay. Let's move on to the next lecture. So for the next lecture, we learn, thank you. Okay, so the next lecture, we learn about first the right-hand coordinates. I feel like we all know that. It's just this, and then you can name like the X, Y, Z, however you want. Based on the system, what's best for the situation. And as like what Christian went through, we need to know the magnitude of Cartesian vectors, which is I hat plus G square root of I hat, well, forcing X direction plus forcing Y direction, sorry, the square root of, okay. The magnitude A X squared plus B will be AY squared plus A B squared. This we all know, and then so there is 3 methods representing the 3D coordinates. Do you guys know what they are? Yeah, one is spherical. Okay, spherical.
I think the second one is directional cosines.
Directional cosine.
The third one would be, I think, unit vectors.
Unit vectors? Okay, good job, guys. They are so for spherical. If we're defining a vector in the 3D space, like it's just out of nowhere, it's just pointing out like, sorry, it's just pointing out like this, but it's not. So if I name this X, Y, Z, it's not in the Y, Z plane. It's just sticking out like this.
Yeah, makes sense.
If we use spherical angles, then what's our first step to do?
Can you show me like where the two angle is like? This is like sticking out.
Yes.
Oh, there's for spherical, there would be a horizontal projection, right?
Yeah.
Across.
So theta and phi.
Yes.
All right.
So yes, good job. So the first step we'll do is we'll take the vector then project it on here. That's a projection of this vector, which my Fy will equal to F cosine theta y. Because we're looking at this like
Just in a 2D plane.
Yeah, in the 2D plane. We're looking at it sideways. So this is well, we can't define it. We're just looking at it. So if my angle's here, then this is
Oh, I see.
sine theta, this is cosine theta. And then when we project it down, then that means we have the f sine theta y. This is the f sine theta y.
Mm-hmm.
And then if we want to know its relationship to the xy plane, then what should we do?
I think you should resolve it like with using the cosine as well, but so I think for the y is gonna be f cos theta y phi
Wait, why?
cos phi, is
Wait.
it?
So yeah, for this one, so it's
Yeah.
gonna be as f sine theta y, and then what do you think?
For the
Cosine
y,
phi, cosine phi.
Cosine.
cosine phi.
Yes, so that's for
Oh yeah.
the y direction, and then for x direction, it would be f sine
Sine.
theta y, and then
Sine
sine phi.
phi.
Yes. So that's how we solve for it. We drew two 2D graphs. And for the next one, directional cosine. That's a lot easier than the one that's the spherical angle one.
Mm-hmm.
Okay, cosine. They will tell us, well, if we see a question like that, they will probably tell us what's theta x, theta y, theta z. They will tell two of us, like what they will tell us two of the value for three of them, and then we need to use the formula cosine.
Are these theta values just the angle between the force and the axis?
Yes, good question. It is. So that's just the angle between the force and two. So basically, if I draw a graph, for x, that would be the angle, and then for y, and then for z.
Oh.
So we only need to remember this formula. Theta squared y plus then theta squared z equals to 1.
I have a quick question. You know, like in I think our first quiz, one of the angle is like 124. It's like beyond 90. Is that possible? Like, how does that work?
So if you have a wait, what do you mean by beyond?
Because
It's greater than 90.
yeah, it's greater than 90.
Okay.
Because I got confused by that one.
Yeah, it's definitely possible. It just means it's pointing not, for example, if this is x, y.
So it's in a different quadrant, basically.
Yeah, basically it's gonna be in a different quadrant, so it will change the way that for example, if it's positive like 23, it's
Mhm.
here, then if it's 100, it will probably be here. So it would change your negative sign, your positive or negative sign.
And I think as long as you respect this equation, then that
It should be good,
yeah.
yeah. And you just plug it in. And for unit vector, I think we all know how to do it, right? It's just if I give you a point somewhere here, and then I tell the distance.
Oh, so this
how
is when we're given coordinates.
Yes,
right?
yes, this is when we're going to give into coordinates. This is 10. If I tell you this is 20, and then the angle here, well, the distance here is 8, then we can, yeah, we
Find
can
the position vector.
yeah, we can just simply find the position vector, which if we name it x, y, z, it would just be negative I plus 10j plus 20. Yes. So that's how we define it.
And then get the unit vector of
And
that
then-
and multiply it.
Yes,
Okay.
that will be go over next chapter, next lecture.
All right.
Sounds good. Okay. So the next one we're going to be going over is moment. Just to kind of reiterate the difference between a particle and a rigid body, a particle is where the size and shape don't have much effect on the system. So basically, it can just be treated as a point, whereas the rigid body, you have to consider the size and shape. And rigid bodies allow for rotation. So that's when moment comes into play. So for a rigid body problem, because we're in static equilibrium right now, we can set all the forces equal to 0. These are the external forces, and then we can also set the external moments equal to 0, because again, we're in static equilibrium. Just to quickly go over the difference between the external and internal forces. External forces are the action of other bodies on the rigid body. So like, for example, a tension force pulling on the object would be an external force, whereas an internal force holds the system together. So like a joint or like, I don't know, do you guys have any examples of internal forces?
A truss?
Yeah, in a truss. So like a two-force member, that would be an internal force.
I think like in chemistry, you have like, metallic
Yeah,
bond,
bonds.
all those.
That's a great
Yeah, yeah.
example outside of the scope of statics.
Yeah.
Great job. Okay. So for moment, we want to understand what a cross product is, because the general formula for a moment is R cross F. Hmm,
Sorry, I have a quick question.
yeah.
Sometimes we use like just force times the distance, and then now let's like R cross F.
Mhm.
If we were only given the distance and the force, like how
Yeah. We just want to make sure that the distance is the perpendicular distance. So yeah, basically this cross product is saying that this R is perpendicular to the force F. So that's very important for the concept of moment, a perpendicular distance. So essentially when we do this, for example, like the cross product of A and J would look like, or sorry, A and B, these are vectors. These are both vectors. Would look like this. And we can solve for that when we're solving for moment.
So what does A and B represent? Does A represent the R and B represent the force?
Yes. So sorry, I did not write that out, but
All right, makes sense.
that's
Oh, I
yeah.
have another question. Would I be able to switch the way I do the cross products? Would I be able to do the cross product of F of the cross product of the position vector? Or does it have to be position vector first?
Like F times R?
Yeah.
Oh,
It should be the position vector first.
yeah, yeah.
Right?
I think if you do the opposite way, you're gonna get like a negative value of it.
Right.
Yeah.
So make sure, because we're not dot producting anymore, we're cross producting. So we
Okay.
get different values. That is a great point.
Another quick question. So for F,
Yeah,
right now I see that it has like Vx, Vy, and Vz.
right,
So does
right.
that mean you have to like resolve the F into like its component, like I component, X component, F component? Because sometimes you have tension,
Mhm.
and do you need to resolve that into like?
Yes. In order to, okay. So when we're doing a cross product here, usually that means we're in a 3D system, right? So basically these forces should be resolved into their components based on the methods that Shelley told us earlier. And that's how we can put it into a cross product. When we're in 2D though, it's sometimes you can just multiply. So for example, if we had a fixed support here, this is a bar, and there's a force being pushed down here, this distance is 2.
Mhm.
The moment about this point would just be, yeah, 2F. And that's the moment. We don't have to use a cross product here. That's a good question. So yeah, again, to reiterate, the R vector is a position vector from the point moment that is being taken about to any point on the line of action of the force.
What
Okay.
does that mean? Can you clarify like to any point on the line of action?
Oh yeah. So let's say we have, trying to get an example here. Okay. This is our coordinate system. And we have, okay, so that looks really bad. Let me redraw. So this is like a bar, let's say.
Mm-hmm.
And then we have a force pulling.
Mm-hmm.
Basically, the line of action of this force extends across this force, right? So if we wanted to take a moment about this point, we could get the position vector from this point here to any point on the line of action. And we would still get the same moment value if we were to take it from here or from here, because it's on the line of
All
action
right,
of the
all right,
force.
that makes sense.
Yeah. Additionally, we can use the resultant I don't know how to say it, but it's called this. So this is just the principle where we can add up all the moments of concurrent forces. So if we had multiple forces here, so F1, F2, F3, we could find the total moment by just simply doing the R cross the resultant forces because they all are concurrent at the same point. So they have the same moment arm. Yeah. And I think that's it for moment.
Wait.
Just oh yeah.
Sorry.
Mhm.
One question for moments. Well, for like force that's going in different directions,
Mhm.
do we use unit vector here? Or
For force that are going in different directions?
yeah, for example, it's pointing like it's sticking like
Mhm.
out like I don't know what angle. Do we have to do unit vector for it and
Oh, yes. We do have to use the unit vector.
then sorry.
Yeah. Do you mean when you're doing components of forces?
Yeah, well, before we do the moment, like for example, I have my force here that I want to cross by R, but if the force is like going in different directions, do I have to do unit vector of it?
Yes. Again, we typically use a unit vector in a 3D space. So let's say there's a plate here and there's a tension force pulling it up.
Mhm.
Obviously, this tension force has all X, Y, and Z components.
Mhm.
And if we were given the coordinates here, so you could say it's like 300, 200, 100.
Mhm.
That's like not very accurate to scale, but we would take the unit vector and dot it with the magnitude of this force in order to get three components so that we could put it in this cross product like this. And then again, we have coordinates, so the moment arm can be represented in 3D with the coordinates. So 300, 200, 100, if we were going to take it about this origin. So that would be the moment.
All right.
And
Can you clarify why we have to do that?
why we have to do what?
Like, why do we have to like?
Why do you have to so we're taking the unit vector of the R or the
Sorry, we're gonna, this is really bad drawing.
All right. I'm
Um,
genuinely asking.
So yeah, basically,
Right, before that, can we just clarify when we have to use unit vector and when we don't have to use unit vector?
unit vector, I would say you use it, okay, always when we have a 3D, you need to separate your forces into components, right?
Mhm.
But unit vector you can only use when you're given coordinates.
Yeah.
Whereas if you're given spherical and direction
Oh.
cosines, you don't use the unit vector. Does that make more sense?
Yeah.
Because if you were given spherical or like direction cosine angles, you use a different method to separate your forces into components. But in terms of finding this position vector to which is the moment arm technically, you should be given coordinates in order to find
All
the
right.
moment arm.
All right.
If that makes sense.
All right.
So we have to always use unit vector for moment arm with given coordinates.
Yes, exactly.
Oh, I thought it was something different. I thought it was to find the components of the force vector and then you do the cross product with a position vector.
Oh,
to the
you're
or-
right. You do
to the
use
origin.
you do use a position vector to the origin.
Wait, can you say? Yeah, okay,
Oh, sorry, guys. We confused you. The only reason you use a unit vector is to separate your force into its components.
So say like you were given a magnitude force and you need to find the moment,
Mhm.
you would have to then find first the components of the force using unit vectors.
So for example, this is
Instead of like say a
let's say
cosine or
So
spherical
OA
angle way.
yes. Sorry, I'm just OA. So the magnitude of this force is F dot the unit vector, right? Because it's along OA. Yeah. But our moment arm would just be
Oh, wait.
the position vector. Sorry. Oh my God, that's supposed to be an OA. So sorry. The unit vector is just the position vector. This is a unit vector and this is the position vector.
So we times the position vector by the whole thing times the unit vector.
Yeah, we
Oh, sorry,
the-
cross.
yes, we cross it. So it would be like this. And that would be the moment about oh.
Is the force here a vector or just a scalar? Because
Oh, it's just a scalar. Sorry. Good catch.
Is the force a scalar?
Yeah, because you would be given like a, say it's like that was, the force was 800 Newton.
Uh-huh.
And
Oh.
Yeah.
we need to find the-
All right, so let's say they give already like F is 300 I, 200 J, and then you don't have to use
Yeah,
it.
then
right?
you
don't
don't use it, 'cause it's a component. This is only when F equals 200 newtons. Where we can't put this in the cross product because it's not a 3D.
Because I always got confused when I used to, yeah.
For you guys.
And then like, okay, this cross product is gonna give you like a moment, but in terms of
Cartesian.
Cartesian,
So
yeah.
it would just be moment x plus moment y plus moment z.
Yeah.
And this is the form that we get because we're cross
And then if you
producting.
want the.
If you want to get the magnitude, you just, Pythagorean theorem.
Alright.
okay.
But,
All right,
yeah.
all right.
Any
That's a lot.
any
I don't think so.
Okay.
How do we do it?
Wait, just press.
Right, so now we're in lecture 6, which is I think taking a moment about an axis, like a specific axis. So I'm just gonna go through step by step. So the first thing we're gonna do is right now we have this F here, sorry, with this F here, right? So we're gonna take the component of that F. So we're gonna split that F into I, J, and K. So once we have that, you're gonna take find the R that connects point C to this any point on this F. So we're just gonna take A because that's the most, because we have the coordinate for that. So we're gonna find CA.
Wait, I have a question.
Yeah.
Could we take the moment arm to point B?
Yeah, we can, because it's in the same force line of action.
Okay.
So we can. So we're gonna find CA to be gonna get the position factor IJK, and we're gonna find the moment about this whole point, which is gonna be CA RCA times F. So once we get the M here, the question asks for us to find the moment about the axis CD. So what we're gonna do is we're gonna find the unit vector of UCD, unit vector of CD. So once we have that, we're just gonna multiply M with the unit vector CD. So the moment about axis CD is just gonna be UCD dot product with M, and that's about it.
I remember this being on the first quiz.
Yeah.
So could we, for the moment arm RCA, could we have also done DA? Because that's on the axis as
Yeah,
well.
yeah, yes, we can. So as long as it's along any axis of the point CD, it's fine. Let's say there's a point K here. So we can take point K to point A or point K to point B. That's
Because
fine.
it's on the axis,
It's
right?
because it's on the
Yeah.
axis, yeah.
Okay, that makes sense.
Oh, so we just dot the position vector?
Yep,
The
so
unit vector.
Oh,
unit
unit
vector,
vector.
yeah. So we're gonna get the answer in the form of I, J, and K as well. And then if you want the like total moment, you can just take the magnitude of that, which is the hypotenuse theorem. Oh, sorry. And that's about it for lecture 6. So
Okay.
on to lecture 7.
So lecture 7 is about force couples. And the general gist of it with a diagram that would give it a better understanding is, say we have a force going here and a force going here. These would be considered a force couple if they were the same magnitude of force. So say they were 800 newtons and then 800 newtons here. The only difference is that they are equal but opposite in magnitude. So we can say in this scale of a XY coordinate, we can say that this is negative 800 newtons, and then this one right here is positive 800 newtons, and that's the general idea of a force couple, is that they are equal and opposite of their force. and of direction.
They also, do they have to be separated by a distance in order to be a force couple?
Yes, it has to be by a perpendicular distance.
Mm.
So let's say that it was like this would not be considered a
Force couple.
force couple because they are on the same line of like of like the
Mm.
force of action.
I see.
So it has to be
Same direction.
Oh, yeah.
so it has to be like a perpendicular distance.
And do they create a rotational effect then, I'm assuming?
Yes, it would. It would like create a rotation depending on what you count as positive or negative.
Hmm.
And another thing about this lecture is for a moment couple. And specifically would be, let's say you had a vector here and a vector here with the force couple going in opposite and equal direction.
Mm-hmm.
And say you wanted to take the moment, we see that they create a resultant distance between each other.
Mm-hmm.
And then we can say that we can take the moment of the force couple to be the vector RB minus the vector RA cross product of F of the force couple. And because they're equal and opposite, we can just say it as it's one whole force. Because it'll just because say we wanted to take the force of this in a sense of like a point, it would be the same thing just in different signs. So we can just generalize it for a force couple and just make the assumption that it's just one whole force to make it easier for calculations, say in a bigger problem.
All right. But I
Any
think like
questions?
yeah, I think like there's a specific like because if you take like from let's say RA minus RB, you have to
Yeah.
take the other F, not this F, right?
Oh yeah, like you're saying from RA to RB or RB to A?
R RA to RB
Yeah, RA to RB.
from point A to point B.
You would have
So
Oh
to
yeah,
do this,
this moment, right?
Yeah.
because this one cancels out.
Yeah.
Yeah.
Any other questions?
I think.
Like, is there anything that you confused of?
Oh, I think also we could simplify these questions. So if there's like a resultant force, we could just we could just cross product the moment arm with that resultant force, as long as they're all acting on the same
Mm-hmm.
Yeah.
point.
Mm-hmm.
Yeah.
All right.
Okay, I think that sums up for lecture 7.
Sure, thanks. So lecture 8 is equivalent force couple. So I have a question for you guys. Basically, if I have three bars like this, and then one is like there's a F here, and then well, this is just think of it as a pin, and then this one is F, and then negative F. And then this is F, and I told you there's a moment F equals to FD. Then do I think those moments are the same? Are those two like what others say the same?
I think these two, like the first and the third one is the same. The second one will be the same if you have a force on this side.
Okay.
Yeah, because
The resultant force has to be the same, and the
Yeah.
moment has to also be the same.
Yes, yes. So if I for second one, if I have a F here,
Then it will be the
that
same.
would be the
Yeah.
same. Yeah.
yes. So that's for equivalent system, there's two things we have to look for. One is F resultant equals sum of the force. The other one is M or O equals to sum of M plus the sum of the moment. Well, sum of the moment created by the force. So the moment that the system that exists on the system, and then the moment caused by the force in the system.
So to check this, we don't set it equal to 0, right? As we
Yes,
do in normal
yes,
moment
remember.
problems.
Yes, we never set it to 0 because we cannot assume it's in equilibrium.
Which one we don't say it to 0?
Or
So
like,
those-
it's not because we're not assuming that it's not in equilibrium, but it's just because we're trying to check that the moments are the same. So when you said this equal to 0,
Do we not set it to 0?
it
Well,
should be the sum of the moments.
It-
Like,
it just says the sum of moment is this equation, doesn't mean the sum of moment equals to 0.
yeah, an equivalent problem is not an equilibrium problem.
Yeah.
We need to remember that.
Yeah, so we cannot assume it's equilibrium. That's why we
Oh.
can't. What if it's static? Wait. So yeah, and then those are the two big component. It was includes 2, and we just have to also check like if the moment, well, the force and the moment are the same in the same direction too.
Mhm. I remember this was on the quiz, and because so basically all the questions or all the systems had the same moment, but the resultant forces weren't the same. So we couldn't assume that they were all the equivalent
Yeah.
system, right?
Yes, yes,
Mm.
sounds good. So basically for this.
Can you repeat that?
Oh, in the last quiz, do you
Uh-huh.
remember the second question?
Yeah.
It asked us to replace the system with an equivalent system, and actually it gave us an option or like a bunch of options with different
Mhm.
systems. And when you found a moment about a point, all the moments were the same. So in that aspect, they did have equivalent moments, but when you summed up the forces, they weren't the same.
So they need to be.
Two conditions.
yeah.
Yeah,
Those have to all equal and then not
yeah.
0.
There are
Right.
two conditions.
And then for this one, if we want to find the equivalent force, we add up those two forces. For the moment, we have to add up this moment and the moment caused by those two forces.
All right.
Thank you. Okay, now we're gonna move on to 2D rigid body equilibrium. Okay, so again, we're in equilibrium here, setting our moments and our forces equal to 0. So the first step for a 2D rigid body equilibrium problem is to always draw a free body diagram. Never forget. This is gonna help you visualize all your forces and see which ones are acting in the X direction, the Y direction. Yeah, just the X and Y direction because this is 2D. Also, for a 2D rigid body equilibrium problem, how many unknowns can we solve for, guys?
2D rigid body
Yeah.
problem. So we have X, Y, and then we have the moment. So 3 unknowns.
Yes, 3 unknowns. Perfect. Because we have these are the equations that we get.
Mm.
And for a 3D, it would be a different case. We would have 6 unknowns, but we're not there yet. Okay, so in a rigid body, there are different supports acting on the system. So for example, these supports are what create reactions or block movement in certain directions. So there's different examples of supports. For example, let's say we have a bar here. Do you guys know what kind of support this would be?
A pin.
A pin.
Yeah, so what motion would be blocked? And in other words, what are the reaction forces?
X and Y translation.
Yes, because notice this bar can't be translated about the X and the Y. So that's why we have reaction forces.
Can I rotate X and Y?
You
Don't assume that.
yeah.
Good question.
Typically in a 3D problem though, we will be dealing with moments. Yeah. So for example, like a fixed support. Oh, actually, to go back to your question about moments. Where would we see reaction forces? Yeah, X and Y again, because it's not translating.
Mm.
But we would also get a moment because it's not able to rotate.
Mm.
So there's a moment here. This moment does not mean that it's rotating. It means that rotation is blocked. It cannot rotate. That's what a moment reaction is.
All right. Makes sense.
Yeah. And then basically to solve, we have to draw out the free body diagram as I mentioned earlier. So yeah, draw. We can just see. Okay. The free body diagram would look like this.
And then the weight, maybe.
Yes, and there's also a weight. Good point. So this is all the forces
Mhm.
acting on the system. And let's say they wanted us to determine
P.
P. Yeah. How would you guys approach this?
I would take moment about the pin, so then it
Yeah.
removes the unknown of F.
Yeah,
Y, and
perfect.
F.
And to get the moment, we could just simply sum up the moments about F. We know how to do that. It's just the force times the perpendicular distance.
Mhm,
In this case, all the forces are acting in the y direction, so we just get the x distance.
mhm.
So it would be, oh, and they're stay consistent with your sign convention. We can assume that counterclockwise moment is positive. So in this case, are we creating a counterclockwise or clockwise moment? Clockwise, yes. So it would be negative.
Mhm.
Let's say our W is 5 pounds.
Mhm.
So P would just be 2.5,
Mhm.
or it would be negative 2.5. That's how we solve. Any other questions?
So if I got P was a negative 2.5, does it mean that P just goes up?
Yeah. Yeah, whatever direction we assume, if we get a negative of that, we have to use the opposite of that.
Oh.
Yeah. So yeah, just my general advice would be to assume positive directions in the beginning, and then this will become more of an issue later, but yeah.
Yeah.
But basically,
Baller.
that's the 2D rigid body equilibrium.
All right.
Yeah.
Thank you.
Mhm. I'll go pause it.
Chill.
Okay, we're recording.
That.
Wait, we're recording. We're
Oh.
Word. Oh, okay, so this is lecture 10. I think we're at lecture 10 now, and we're looking at 3D force equilibrium. So I'm just gonna go through, like, I think one of the major component of this lecture is like recognizing all the different joint and all the what like the reaction for each joint is. Because before we look at pin joint, and it's very simple, it's like 2D motion. But for 3D, you can resist the movement in three direction and three axis of movement. So it's gonna be a bit more complicated. So here I have like a list of like all the different joints that we have. We have a ball, we have a roller and rough surface, roller on rail, rough surface, ball and socket. So basically you can go through each one of these, and we're gonna link this, and you can go through like see each reaction for each of the joints. So you can recognize like when you have a problem and you want to do like a 3D force equilibrium solution. So the first thing you want to do is like actually recognizing the different joint that you have. And with that, you can identify what reaction force you need to include in your free body diagram. So when solving for 3D equilibrium forces, you can basically solve for three unknowns. You can do sum of force in x direction, sum of force in y direction, and sum of force in z direction. And you can also make moment about the z-axis, sum of moment about the z, sum of moment about the y, and sum of the moment about the x. So you can create three different equation, which means you can solve six different equation, which means you can solve for six unknowns. So that's about it. It's basically the same concept as before, but it's on steroid.
Wait,
Yep. You have any question?
on the last quiz, there was a
Mm.
free body diagram question,
Uh-huh.
and I believe it was like a journal bearing.
Yep.
Could you go over the free body diagram for that, please?
Journal bearing. Is it the one with like
Yeah.
Oh, all right. So it's basically this one. This is like a journal bearing. So you're gonna have like moment about the X, Y, and Z, right?
Mhm.
So that's the reaction force. And for the moment, you can see that this thing can rotate around the x-axis, right? So there's not going to be a moment about that, about x-axis. Basically, right now, this joint is preventing rotation in the y. Sorry, this is z. This is z, and this is y, and this is x. So it's preventing the moment about the y-axis and the z-axis, because this joint is like making the pin stuck to it. And you can rotate it about the X, but you cannot rotate it about the Z and Y. And then there's also, yeah, that's about it. Make sense?
Okay, thank you. Yes, that makes sense.
I think on to the next person.
Yeah.
So the next lecture is about trusses. So characteristics about trusses are that it's in 2D, or at least the way we analyze it. Generally in the class is that it's 2D. A lot of the assumptions that we make are that all the applied loads of the truss are going to be at the joint itself. So for example, let's say we had a number of joints going along this design. The applied loads would not be in between the joints. Instead, we are assuming that it's only at the joints itself. Another assumption that we make is that a truss have two force members only, meaning that let's label the above the image that we have as A, B, C, D, E, and then F. Instead of saying that A is like a force going here, and then B has its own force of B, and then A, they are two pinned together joints. So, and because there's no interfering force in between the joint, the member, we can just say it's one force only. So we can say it's AB, force AB. And this allows us to simplify a lot of our FBDs and help us solve a lot more unknowns, because if we just let it be by itself for, let's say, complex problems, we would have too many unknowns, and we wouldn't have enough equations to solve for every unknown. So that's why we make those assumptions.
So if there was an applied force, would it still be a two force member? If
It would not.
yeah. It wouldn't, because then it would not be a two force anymore, because I think two force means it's just the internal forces.
Yeah. internal
Um,
forces.
Right. So if there is an applied force right here, if you could draw that,
Yeah.
like, yeah, that would not be a two force member, because now this FA is creating
Another force.
another force. Yeah. So it's kind of disrupting this internal two force member that we have going on. So yeah, that's an important point.
And then another type of force member that we have to consider would be zero force members. And then those are the members of the truss that carry no load and are actually there to add stability. So in this case of the design, the zero force members would be points A and F. And although they do not carry force, you do still need to consider them in your FBDs and equilibrium equations, because if you did remove them, let's say this was taken out, the system would then be unstable, and say like a real life problem, like it could collapse with A being removed. So that's why we still keep it in our FBDs and
The design.
yeah, in our design. So there are two methods to solving a truss problem. One is the joint of methods, and that's generally a very
The method of choice.
method of joints. That's very inefficient method for more complex problems. It can work for like more simpler trusses. However, if you get one of your joints wrong, then the whole system that you did after is just going to be wrong. So instead, a lot of the method that we do in this class a lot is the method of sections. So the method of sections would be, let me bring down this image. say we brought down the image and we wanted, and let's make it into a more realistic scenario. Let's have this here, and the only applied loads are at C and E. And we wanted to find the force in from A, B here and here. Oh, here and here. And let's label that B. B, and that's B. The section of joints, method of sections would be cutting through the joint itself. And you can only have 3 physical forces in your FBD, in a separate FBD. So it would be D here, and then C to A. But something that we can do is imagine having the forces there. So because we're assuming that AB would be a force member, it would be FAB to B, and then also A has reactions of AX and then AY. And then this one also is a force member because there is an applied load, so this is not a force member. And then we would, based on this, we are able to either take a moment about a point to find, say, like a unknown at FAB, because then for this example, we're assuming that they're all right angles, so we don't have to worry about that. We can just say the angle is 45, so it's just going to be 1. So we can just do straight multiplication. We don't have to consider cosine or sine. And you would just set up either, depending on what you need, force and moment, equilibrium based on a point that you want. Are there any questions?
I think when you section this part, when you section this part,
Yeah.
it's gonna look something like this now. You're gonna have a force here, force here, force here. You're gonna
right.
get AX and AY,
AY.
force here.
Yeah.
So then these are the 3 unknowns, and you can take a moment about like this one,
A
and
to get rid of
this
it.
is gonna cancel out because it's in the same line
Yeah.
of motion. So you're gonna have these 2, and probably you can solve it with
Mhm.
like some of Fx
Yeah.
and Fy.
And typically when we take a section, it's usually through an unknown force, right?
Yeah.
So, yeah. Okay.
Wait, sorry, one question.
Yeah.
For the zero force number, can you explain more? Like, what do you mean by like the zero?
I think there's 2 conditions for it, right?
Yeah.
So only
Yeah.
to like,
So like no applied force has to be present at the joint itself. So it just has to be its reactions only. And then both of the members have to be zero force members. So in this case, the zero force members of the 2 are A and F. And there's no loads interfering in this line.
I think one would be,
If you,
if we go down here, a zero force member would be like this,
Yes.
right?
because this won't be
Oh,
a
yeah,
zero
that's
force
true.
member because there's reaction force. There
Yeah.
can even be
Oh,
like
yeah.
a reaction force or
Oh,
a effect
okay.
force. Yeah.
Yeah, or like this, like any one of those. Because, yeah,
Okay.
because they're connecting or joining.
and there's no reactions and there's also no applied forces there,
Mhm,
so
mhm.
it would be 0.
And then for the third, like that's if it's like connected with 2, but if there's 3, 2 has to be non-collinear, and 2 is non-collinear, and the other 2 is collinear. I mean, 2 collinear and 1 non-collinear. So it's like and like that, right? So these 2 are like collinear, and this is non-collinear. So that's for like 3.
Okay.
It's like 3 joints
So the
together.
non-collinears are zero force members.
Yeah.
Okay.
Nice.
Thank you, guys.
Okay, now we're moving on to frames and machines. Okay. So let's just go over the definitions first. We just went over trusses. These are composed of all 2 force members. and they don't move, they're stationary. Frames are a mixture of two force and other members, and they are generally also stationary, whereas machines mix both, but they will move. So like a truck, the backhoe example, in one of the homeworks. The general method to solving a frame problem would be to, usually what I do first is I take it apart to simplify it as much as I can. For example, this was a problem in the homework, but it's kind of like an A-frame thing. And we have pins here. First, draw out the free body diagram, of course. AY. Yes, BY. Yeah, if we wanted to find like the reaction at A, let's say. Okay, wait, actually scratch that, sorry. Basically, first take it apart, and if you're given a known, I would start with that member first. So we know what the value of P is, so I would take this apart and just analyze this member by itself to get the values that I need. And then, wait, sorry, let's say there's like a slider here and there's a force B.
Slider sliding the thing.
Yeah, wait. I have to add another force here.
Yeah.
A pin, yeah. You can add a pin.
Okay. There's also a pin here.
And
Sorry,
together.
this drawing is really, yeah. Okay. Basically, we're going to take that member apart because we're given a known value for P. We could just say that's 8. No, we're going to say that's 1 to simplify. BX, BY, these are all pin supports, so we have just a vertical and a horizontal reaction. So we could take the moment about C in order to find BY. I'm not going to go through like the entire thing, but basically you could find BY through this because BX cancels out when you take a moment about C. And also C's, you don't need the C's to take a moment about C because the moment armor would be 0. And then once you find BX, you can create an equation which looks like this. Just sum all your forces up. Equals 0. Then you could find CX, and then you can also, or sorry. Like this, and then you would be able to find, oh my gosh. And then you'd be able to find CY. And now that we have that information, we know the direction of BY. Oh, this is also a really important point. So let's say we got a positive value for BY. That means we assumed this in the correct direction, right? So it would be pointing up for this bar. However, if we isolated this now, this right-hand section right here, this is where B is. It would have to be pointing down because they like oppose each other. I don't really know a good way to
Isn't there
explain.
law?
Yes, it's Newton's third law, like equal and opposite reaction forces. So let's say for this member right here, we assumed correctly and BY is pointing up. If we were to take apart another member to analyze and find another reaction force, we have to set it in the opposite direction. So again, if we got BX to be positive, now for this member, it's negative. So it'd be like this. Yeah, and then you kind of just continue to take apart and simplify the frame as much as you can to find the unknowns. Also, another thing that could be helpful is finding a global equilibrium equation, which is basically just taking all the applied forces and not the internal forces. So in this case, the reactions that would be present in the global equilibrium would be A, the bottom two, A and B, and also P. Those are the only applied forces we have. Everything else is internal. So that's another equation that can help you solve for the unknowns. Yeah, and adding another equation gives you more unknowns that you can solve for. Do you guys have any questions about frames?
Is it important to identify like, oh, is it like a truss? Is it like a
Oh,
frame?
two-force member. It is very important. I guess when you first start with frames, you should identify the two-force members because it's going to simplify your process. If you know that there's a member that there's just two forces and they're just opposite in direction, we can simplify it and eliminate the number of unknowns through this. I think Christian talked more about it before. But yeah, and we also know that the direction would be the opposite. So if we solved,
Do we have a two-force member here?
we don't have a two-force member here. So yeah, this is not a good example to talk about two-force members. But again, identifying two-force members is important. Actually, we can, on the topic of that, we can move on to machines because machines have two-force members. So a machine is similar to a frame, but it's a moving problem. That doesn't really have much effect on what we have on the solving process, but if we had a truck,
I can do a picture now.
wait, let's pause it. Okay, we're back with the picture. So this is a machine problem. Let's first identify the two force members, because by identifying the two force members, we will be able to like simplify our calculations, you know?
Can we like guess first and then
Yeah.
tell?
So what do you guys think?
I think a two-force member would be FH maybe.
Yes, FH would definitely be a two force member
Mm-hmm.
because as you can see, there are no applied forces and it's completely internal. So yes, AB. AB is not because there's a pin, right? So it's not.
Is it not?
Is it not?
Oh,
It's a pin, but it doesn't have like a reaction.
It doesn't.
wait,
Like
you're
it's a
right.
reaction if you open up the pin.
That's my bad.
Yeah.
AB is a two force member.
Mm-hmm.
Ignore what I just said. DC is also a two force
Yep.
member.
BCE is not. Oh, it's not.
BC
No,
is not
because
because there's
C.
C.
All right.
So those are our two first members. And then basically when we draw it out, they can be simplified kind of like this.
Mm-hmm.
As you guys can see, they oppose each other in the motion. Okay. The first thing I would do is what known do we have here?
The 300 and 3,200.
Yes. So I would isolate that.
And take the two force member.
Yeah. Let's say we wanted to find the force AB. I would just isolate this portion. And then we know that there's
Yep.
and then I would analyze by taking a moment about A. And that way I can find the reaction forces. Wait, no.
Wait, don't have to take like
D.
this with you. No, it's a good learning process.
Yeah.
Yeah.
We all struggle with machines.
Yeah, we all struggle with machines.
Yeah.
I think it's maybe in the DC, right?
Yeah, I think so.
Yeah, this should be maybe. I mean, why don't we include DE though? Why don't we include something?
Oh, that one? Because I think that's would then be
Wait.
too many unknowns to the moment.
Oh, sorry.
Or is that
Yeah,
the-
okay. So basically our point, the objective here is to solve for AB. We don't want to take a DC into this because then we're also going to have an FDC, which is another unknown, right?
We can take whatever we want to.
Yeah, but if you take
Yes.
like this two out, then you have to like open up the joint. So that's gonna be like a joint.
Yeah.
ds and dy, right?
We could also draw out.
I see.
Because you're taking it out, so now you have to find the reaction force
Mhm.
for that.
Then why is the top FAB and then the D point is just dx dy?
Because we didn't
wouldn't-
take out the entire, we didn't take, oh, sorry.
Because FAB, we're just like, let's just imagine you're cutting this off,
Yeah.
but for D, you're gonna remove all the joint. And then the ds and dy will take into account all the other forces. You know what I mean?
Is it because AB is a 2 force member?
Yeah.
But
Yeah.
isn't, aren't we saying that DC is a two-force member as
Wait,
well?
yeah, okay, so I didn't really draw it out, but what we're isolating is this. We're not taking,
Yeah, because if you take A out, if you take this out, then you're gonna have AX and AY, which just adds to the unknown. Right now,
exactly.
you only have like AB.
So when we take this entire member apart, now we have a force AB. Whereas we're not taking DC, we're not including that in our free body
Mhm.
diagram. But I guess right now we could say that this is like an external force now because it's a reaction. This is a pin. We're just taking the pin apart. We're not taking DC with it.
We can choose that. You just choose what we want to take
Yeah.
apart.
Yeah, because this
Okay.
is they're connected here by pins.
Oh, okay.
So if we just take it out, then
It doesn't matter.
Yeah.
Because if you cut this out, you can put like DC as a two force member,
Yeah.
but for DFG, you can't just simply put like that, you know? It's gonna
yeah.
be a bit more complicated.
Oh, you can't even simplify the internal force like that.
Mhm.
Yes. So again, two force member is very important to identify because we can make these simplifications. Yeah. So here we could take a moment about D and our D's would cancel out and we could find FAB. If we didn't identify it as a two force member, we would have had an X component for FAB and a Y component. And that would be too many unknowns to solve for.
Mhm.
So now we can solve for FAB. And you basically follow that entire logic process. Like for example, for FH, I probably would take a free body diagram of this entire thing. And now notice how when we take a free body diagram, all these forces are internal. This is internal. Everything going on is internal, except for the force at H. Could you guys kind of see that?
Yeah.
So we can draw that in our free body diagram and therefore solve for it. Everything else is like internal. Our bucket weight is external though. It's applied. It's an applied. So the only things that we have to worry about are the force FG as well as this bucket.
Wait, now I have a question.
Yeah.
Let's say theoretically we do cut here, right?
Mhm.
Then we're gonna have like FAB and then FDC and then can we put FDE? Can we do that? But then it's gonna be hard.
That's only if you take a cut, including this.
I don't think you
Right.
can do that. This
Really?
is not a trust.
Mm.
You can second
Oh.
that's why we can just cut it.
Yeah.
Because it's not a trust. You can the whole reason we do two force member is because
So identifying two force member is also like determining where you can cut.
Yeah.
So for example, like D you can't even cut, so you just take the whole thing out and put the reaction force of
Yes.
dx and dy.
Oh,
Yeah.
yes.
It makes sense,
okay,
right?
yeah,
Because you can
makes
cut.
sense. You
You
can
can
cut
cut.
it, so you
Take it
just
out and put ds and dy, because in the end ds and dy will take
Will be
into
the
account the
same
other
thing, yeah.
forces. Yeah.
That is a very good point.
That is a
When
really
we cut here, it doesn't really matter what we're doing with C because the reactions dx and dy take into account that
Yeah, the
reaction
two
at C.
forces, yeah.
Yeah, because this is a two force member. So we're accounting for it. And again, like that's the simplification process
Yeah.
that
Because if you remember in our last quiz,
Mm-hmm.
when there's the force P
Mhm.
that didn't show up in the other
Yeah.
reaction force, right?
Yeah.
So because the reaction
Yes,
force in
it
that,
absorbs
it
into
absorbs,
the
yeah.
reaction force.
Yeah, yeah.
Yes.
All right.
So yeah, the general approach again, just take it apart. When whatever knowns were given, take that apart first and then work outwards from there. Identify the two force members so that we can simplify. And then yeah, usually you create force equations for like the applied loads. Actually ignore what I just said there. Yeah, that's
Right.
how you go about it. Any questions?
I think we're good.
I think we're good, yeah.
Yeah, exactly.
Sorry, that's a little bit more of a complicated topic.
No, I think we learned a lot.
Yeah. I
It's
think the
good.
approach method is really important too,
Yeah, approach method.
because you can get very overwhelming real quick.
Yeah.
Ooh, okay, so we're gonna jump into friction.
Mhm.
So friction is really interesting. Well, okay, so for statics, we almost like always use US for the problem we're solving because it's not moving. It's like we're basically using the point that greatest force is applying that it's not moving. Because when the object starts to moving, it's gonna be a what was it? It's gonna be kinematics force. Kinematics coefficient that we need to know. So imagine I have a P here, weight, and then normal force N, and then friction F. So the maximum static force equals to F equals to mu S. And that's the normal force that the box have it. Okay. Okay, so
Wait, did you mention that it opposes the motion?
oh yeah, okay, so basically the friction opposes the motion. So whenever we have a friction, for example, even if we're on an inclined surface, our normal force pointing this way, the motion is going, if this is force pushing down, then where does the friction go?
The other way.
It would just be opposite.
Yeah.
Yes, so friction is always opposing the motion, the opposite of the motion direction, FBT. And then for a different situation with friction, well, basically, the motion is when our P force in the x direction is greater than Fm.
Because that would mean the applied force is greater than the friction, so the friction
Yeah, the
cannot
friction cannot.
block movement because P is greater.
Okay.
Wait, what about for equilibrium? Or what about for equilibrium?
Okay, so for equilibrium, our px is always smaller than force.
Can you
Than
clarify
the
what
friction.
PS is again?
Yeah, so sorry, px is here. Well, this is p.
It's the force
And
that's
then-
causing the motion.
Yeah.
Oh,
So,
alright,
yeah,
alright.
so
And
P
F is the
is-
friction force.
Yes.
That's p1. Yes. So the px is
Mm.
greater than the force.
Yeah, it's like the applied force that's
Mhm.
causing the block to move.
Mhm.
Yeah. And if we have motion impending, what would that entail?
So for motion impending,
This just means motion is about to begin.
yeah, I
Mhm.
believe.
Yeah,
So we
if
have the
you
normal
increase the
force
force by
here,
0.1.
and then we have the friction here. So motion impending would be, okay, first we separate the F2x and sorry, this is y. And the px direction, so we can analyze force better. And then for motion impending, px in the x direction will equal to F friction. So motion is impending one Newton more force applied, the blocks are moving.
Alright, and then can you talk about the normal force? What would it be? Because you would require to know the normal force.
Yes.
Um,
Yes, yeah, that's a good point. So the normal force you would require to know to find friction because the formula of friction is mu statics times the normal force that's blocks it. For example, if we have an inclined surface, well, this Fn will be need to find on the x-axis with angles.
mhm.
But that's how.
And like for the PS, you have to take into account like the downward motion, right? So PS, the y component of PS plus weight will equal to the normal force,
Oh,
right?
yeah. If you're analyzing FVD, yes, it's gonna equal, because you sum up all the force in x and in y direction.
Yeah,
Yeah.
alright.
For an incline, you should, take into
Yeah.
consideration that angle.
Always find the normal force, always look for the normal force.
Yeah.
Yeah, that's about it. For 15 minutes. What's up, guys? All right, so we're now at lecture 14. Let's go. So first of all, we're gonna talk about like few definitions in chapter 14. I mean lecture 14. So wait, sorry. Definition. So first we're gonna have like a definition for center of gravity. So basically, center of gravity is like a point which locates the resultant weight of a system particle. Usually, we're so used to be like very simple objects, so the center of gravity is just going to be there. And then the second one is the center of mass.
It is just in the middle.
Yeah. So center of mass is like where a point where all the mass is concentrated upon. Again, for like a very simple object like this, it's just gonna be like right in the middle. And then we have centroids, which is geometric center, which we also call centroids. So these three will be equal to each other if and only if the material and the gravitational field are all homogeneous. That means that the density of this material is equivalent in each point of slice, and the gravity force or like the gravitational pull is equivalent in every single surface area of the object, if that makes sense. Yeah. So moving on to the next one, we're gonna find like yeah, this one.
So are the stuff that we're dealing with is like
Yeah, we're gonna like,
homogeneous?
yeah. So we're gonna assume this is homogeneous. So like if I find like the center of this, that's where it's gonna be. That's where the center of gravity and everything is gonna be. So we're gonna be determining the centroids by integration.
Is this a certain method that we have to use when we have curves?
Yeah, for like graphs and everything, you want to use this method. So basically, you're gonna have S. Wait, all right. SA equals to
Can you put the A on the bottom and divide it by
yeah. So this is like for the S, and then the YA equals to SYDA. So when we want to find the centroid, you're gonna go like that and divide it by A. And then for the Y, it's gonna be the same, YDA over A. Wait, quick question for you guys.
Yeah.
Actually, it's for me. Just to reconfirm. Isn't there like an integration on the bottom as well?
Yeah, to
Like
find the
DA?
area, it's the area under the curve.
All right,
So
yeah.
area is the same thing as the
All right,
integration.
yeah. So the area is gonna be like the integration of this. So it's gonna be like integrating DA.
The only
So-
difference between the numerator and the denominator is that you multiply by x.
Yeah,
and
S and Y.
y, yeah.
Yep. So let's say we have this graph, right? So to solve for S, it's gonna be integrate S dA over dA, right? That's great. So dA, we can put it as, we can do a double integration dx dy over dx dy. But we can also make it into a single integration by removing dx. So dx is just basically the difference in the x-axis, right? So for x, that means like from this point, like specifically for this graph, it's going to be like from this point to this point. Does that make sense?
Yeah.
So from this point to this point, that means it's going to be from
So a horizontal slice.
horizontal slicing. That you are correct. So it's going to be from x squared to
X squared. Oh, sorry, root of x.
wait,
It's
is
gonna
it-
be x squared minus x. And then from
yeah.
0
Wait.
to 1.
But isn't it root of x integrate it? Oh, when you like switch.
Yeah,
it
it's gonna
to
be
the other
it's
side?
gonna be like s and then the s you're gonna replace it. Let's say we replace it with y first. So y this y minus y squared
Wait,
dy,
no. You have to
and then it's
you have to
just
solve for x
Yeah.
in terms of Wait.
But in MAE,
Okay.
if you did a vertical slice, you would have to solve it
Yeah.
for the upper bound.
So when we're doing the centroid for the x, you have to use a vertical
Oh,
slice.
right. Yeah.
So it would be like this. And our bounds are from 0 to 1. And then,
Wait, this is for the.
oh shit. Oh, I can't say
It would be easier to do a vertical slice, but you can do a horizontal slice.
Or.
The bounds are just a little bit more tricky to figure out in terms of x.
Hmm.
The reason why a vertical slice would be easier is because we know that the lower bound is always just going to be the x-axis. When we do that vertical slice, so we only have to take into account.
No, even if we do a vertical slice, it's gonna be from this bottom graph to this upper graph
Yeah.
Yeah, but then we can just say it's from this line
to
to that
this
line,
line.
to that upper line.
But
Yeah.
isn't our centroid equation just this? Because for the centroid, for the x, we have to take a horizontal slice, right? And it would just be the right graph minus the left
Yeah,
graph.
this makes
Yeah.
sense.
From
Yeah,
zero
yeah,
to-
yeah,
yeah.
yeah. Wait, dx or dy?
It's dx,
Oh, because
because we have an x. It needs to be in terms of x.
Yeah, because otherwise
Mhm.
you can it would just be
all right,
one.
it makes sense. It makes sense. And then for the y, you do the same thing, but you take the y term. So for
Wait. This is square root of x, right? Why wouldn't it be square root of x minus x squared?
Wait, why do they give it to us like this?
Because
Because they changed it in terms of y, because it's y squared equals x.
wait, I swear to God, I did this just now, and it all makes sense.
Well, but like
No, you are right,
you-
because
because
it does turn into x 1/2
it would
minus x.
and then x squared. Because that's just how the math works.
Can you write down?
Yeah, so this would be 1 over 2x squared. Because
No, I think,
No, it's x squared minus x 1/2.
oh
yeah.
yeah, it's x squared minus. Wait, why would it be x squared minus x?
Oh, because we're solving for y. All right. Yeah. Yep, it makes sense. Because
Wait.
It's x 1/2 minus.
Yeah,
That's wait, no, but that's for a vertical slice. We're doing a horizontal slice.
Wait.
Yeah, for a vertical slice, it would be x 1/2 minus x. The top curve minus the bottom curve.
Yeah,
But
or
since you're
the
doing
right
horizontal,
side
we do
minus
the
the
right
side.
side minus the left side.
Yeah.
Yes. Sorry for the confusion.
Okay, so it's x squared minus x.
Yeah.
Because we're taking vertical. Okay, sorry.
Yep.
It was
S squared minus x 1/2. Yep, this is correct.
x squared minus x.
1/2.
1/2.
Oh.
Because you want to be like y
Yeah, you get it in
minus
terms of y.
y
It's
minus
y
y.
squared.
Oh,
Yeah.
in terms
So
of-
basically, you want to make it like
Okay,
y2 minus
it is
y1.
Give it to us in terms of
Yeah.
y.
All right.
Yeah.
All right. So and then for the y, it's just gonna be 0, 1, 0, 1. This is gonna be the same dA, and then for the upper one. So instead of before we change the y, so now we're gonna do for the x. So it's gonna be yep, y squared minus
Y to the 1/2.
1/2. Yeah. And then it's gonna be dy, and then the bottom one is gonna be the same as before.
Wait. How did we get y squared minus one?
Because this is the top.
Then you solve it, yes, you solve it for the s.
Oh.
Yeah.
Like,
So basically
that's when
you're
we do a vertical slice.
yeah, basically you replace like dx and dy. So dx is the difference. For the first one, we replace dy, right? So we replace the change of y. So change of y is just gonna
Or
be
like you replace dA.
yeah, dA with dy
dA
dx.
with d. No,
Wait,
no, okay, so the original equation is right, and we
Uh-huh.
don't know what dA is.
yeah.
But for the x scenario, dA would just be the difference in when we take a horizontal slice. It would just be the difference. So it would be x squared minus x 1/2 dx. That's what you replace it with.
I thought we
dx, not
replaced
dx.
yeah, we replace dA
Isn't left minus right?
equals to dx dy, right? Oh really? Is it not the same?
No, because you
what's
could see-
not the same. Explain.
Sorry.
No. No worries.
See, it's like this. It's not dx dy. That's for like triple integration, double integration.
Yeah, that's
See,
not
this is what we're not trying to do. We don't want to use double integration
All right,
because
all
that's
right,
too
yeah, yeah, yeah,
complicated.
yeah.
So this is why we're using direct integration.
Oh, that's what you said. Oh, you were trying to use double integration.
There's
Yeah.
another method where we use double
Oh.
integration, but we're showing that that's too complicated. So
Yeah,
we're
so
doing
you're
this.
single
Okay.
integration. Oh, all right. All right. So
Wait.
if we use the double integration, it's gonna be like integrate x dx dy, something like that, right?
Mhm.
Since we don't want to use double integration, we use like the substitutioning. All right, yeah, makes sense. I hope that all makes sense to you guys. I'm sure if you work along, you can figure out like where we find our mistakes, and you can learn from that. Moving on. And then we have like centroids of common shapes and area. And I know that Professor Chi mentioned that she will provide this graph in the exams. So that's gonna help us a lot.
Wait, composite bodies.
Yeah,
Composite bodies.
for composite bodies, let's see, you have like a um
Wait, I'm sorry.
gonna cut this off.
Wait, wait.
All right, so for composite centroid, basically you're gonna find let's say this is number one, this is number two, you're gonna find the first centroid, and then you're gonna find the second centroid, and then for the composite centroid, you're just gonna add these two centroid together, and that's about it.
Wait, but you should also use the equation.
So it's just
Oh
this.
yeah, 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 and that's about it for the centroid.
Yep. Okay, moving on to distributed load.
So distributed loads would be, say, you have a good example of it would be, say you have okay. It's trying to explain how can we have like a concentrated load onto a let's say like a rigid body, and how can we then distribute it across the entire area of the concentrated load. So say let's for example we have a beam with a roller with a with a roller and a hinge, and let's say the load is covering this area. And here it's 12 kilonewtons, and then here is 8 kilonewtons. We need to find how are we able to, instead it being concentrated at this point, so instead of it being at these two concentrated points, it's now across the entire area below it. So that would be what we call the resultant force for the distributed load. So the equation would be equal to the summation of the area that we find under here. And let's say that we were given the measurements of these segments. And an easier way to find it would be to split it into shapes that we are comfortable with, and to then find the area of each section that however way you sectioned it off, to find the area with the, depending on, so like here would be 12 kilonewtons, and then this side would be 8 kilonewtons. And then you would find the area across their load, across the area under here, and then that would be, after adding them up, that would be your distributed force or resultant force. And then say we wanted to find its location, it would be the we would have to find its centroid, and that would be the summation of all the local x's of the area of the joints
Of the shapes.
of the shapes, sorry, multiplied by the areas that we found separately, divided by the area, I
The sum of
believe,
the
the
areas.
sum of the areas,
Should draw the.
and then that should be how we find its location. And that's about it for distributed loads. Are there any questions about that?
So basically like distribution of load is like
We're just trying to simplify it into like a resultant force, right?
Yeah.
So from a distributed load, you want to simplify it into like a single force
Yeah.
and
And you can also
the
find the
area.
moment, I guess, because
Yeah.
the location times the area is technically, it gets you a unit of newtons times meters.
yeah.
Yeah.
So
Yeah.
that's the
I mean,
moment.
centroid is basically you finding like the moment of each
Yeah.
point
Yeah.
and everything, right?
Mhm.
Yeah, I think that's good.
All right.
Good job, Christian.
Thank you.
Hey, moment of inertia. Yes.
Let's go.
Yes.
So does anyone know what moment of inertia actually measures?
The moment of the inertia.
It measures the body's resistance to bending or rotation. That's the physical meaning of it. Might be helpful when we do the
Wait,
mathematical
wait,
analysis.
so if
You're
I
preparing
wanna-
us for the real world
Yeah,
situation.
preparing for the real world
Wait, so
situation.
if I wanna like rotate this, that would
We
be
have an
only-
iPad. Yep. We rotate it? Yes.
Oh,
Right. Oh, actually, no. That's not a very good example, but so we can balance this. Okay, actually, that's not a good example. No, but it has to be like harder to, oh. So when I'm away from the area, the concentration, it's easier to bend. Well, it's not bending, but it would be easier to bend than bending it from here.
yeah, yeah.
Notice how there's a
Yeah.
lot more resistance,
Yeah.
whereas if we're further, it's easier to bend, supposedly.
Oh,
Yeah, yeah.
yeah.
So, okay. So now on to the actual calculations. We've been here for like 3 hours. Okay. Anyways, so we can use a method of direct integration usually if we're given a graph. So for example, let's say we have a graph that looks like this. This will also be helpful to understand like horizontal and vertical slicing and stuff. So we have a parallel axis theorem. Wait, actually the parallel axis theorem does not come into play here, not right now. That only comes into play when we have composite bodies. But the moment of inertia about the x-axis, this is the general form. So when we are finding about the x, we always want to take a horizontal slice. So that's gonna look like this.
What's funny about the X, we take a horizontal slice?
Yes, for the moment of inertia,
Yeah.
not for the centroids.
Because
though.
centroid is x in
Yeah.
x, and this one
But
is
here
y.
it's not y.
It's opposite. Yeah.
So in this case, dA would be dx dy, and our dx is just x, or sorry. It would be y minus y squared, because we can also,
Yeah.
yeah, and then dy. dA equals dx dy equals that, okay? So then we plug that in. What would our bounds be?
B, 0 to B.
Yes, 0 to v, because it's a horizontal slice.
Yeah.
So we want to take the bottom to the top, right? It's kind of counterintuitive because when you're doing when you're finding the dA equation, you want to take the right minus the left, but the bounds would be the top and the bottom.
Yeah.
It's like a little bit, yeah.
It does make sense.
But yeah, that's basically the method of taking slices and direct integration. There's also a parallel axis theorem for when we have more complicated shapes, not complicated, but shapes that you can split up. So for example, like this. The moment of inertia about the x can be represented as this equation. So this is basically, yeah, okay. We know that the axis of least moment of inertia for any body is the centroidal axis. So we're going to be taking a moment of inertia about the centroidal axis. I have a question for you guys. If you wanted to increase the moment of inertia without increasing the area, what would you do?
I would push the material as far away as possible from the centroid.
Yes, exactly. So that gives us like a more conceptual understanding.
Real
But
life
anyways,
problem.
yeah, real life problems connecting. Defined for a composite body, we want to, okay, wait, this was already separated. Say we're given this, right?
Mhm.
What can we split it into?
A triangle and a square.
Yes. And we're given formulas on our formula sheet for the moment of inertias for these complicated shapes. So for a square or a rectangle, it would just be this. And for a triangle, it would be yes, and I believe there is no y moment. It would be 0
Oh, really?
for
Wait, why is that?
y. Let's see it.
Is it just because?
I mean, I know it's 0, but I just don't know why.
For a
Alright.
triangle?
For a triangle, yeah. The moment of inertia about.
All right, it makes sense.
Yeah. Just follow the formula sheet. Okay. To find this, first we want to find the local centroids. Mohammed went over that in the composite bodies. So you basically want to sum up, use this formula to find the centroid. And then when we have a value for that, let's say we get to, this is when we do the total centroid for this. We want to plug, so we're going to use this value. This is for shape 1. This is for shape 2. Let's assume we're given like a base and a height value. Our dy would be the distance of the local centroid of shape 1
Mhm.
to the centroid of the entire thing.
Mm.
So let's say,
Oh, so you have to first find the center of the
yes,
whole composite
you want to
thing.
find the centroid of the entire thing. Let's say this was 1. But for example, this is like 4. What's the y centroid for this? 2. Yeah, so it would be 2 minus 1. That's how you find it.
Oh.
And then you do the same thing for y. And then to get the total moment of inertia about x, you want to sum up the value for number 1 and for number 2, the shape for number 2.
And then the A is
The area. This is
Alright.
the area. So
area
that's
for the whole thing.
no, for the shape that you're analyzing.
Oh.
But you have to do another
Another step
calculation
for the
too, and then you add it. You
Oh.
add this total plus whatever you get here. And that's for the x, the moment of inertia about x, and then for the moment of inertia about y, you did the same process, but you use these values.
So
Alright.
what is 1 again for the centroid? What's that centroid?
This is for the entire thing, when we add up the centroids for both of these.
Oh, okay.
Yeah, when we're doing like the chart, you
Yeah.
know, and yeah, that's the value that we
So
get.
that's sum with
Yeah,
everything.
the entire centroid for the entire
Okay.
thing. But our 2 is just for this shape. So this is the distance
Okay.
between, yeah.
Okay.
Do you guys have any other questions?
No, explain perfectly.
Perfect. Moving on to rectilinear.
So for rectilinear, we're jumping from statics.
Ooh. Real life. Whoa.
So we're right here, and we jump to dynamics.
Why is it that?
No, that means we
So
complete.
we are dead
Oh.
right now. We've been here for way too long, but
It's okay. It's okay. Transition. So we're gonna use kinematics.
if you're a TA and you're watching this and you made it this far, hi.
Good job.
Great job.
We
We appreciate everything you do. Thank you.
do.
Professor Chi, we love you.
Yeah, Professor Shi, if you're watching this, thank you for teaching us this
Tune
part.
in.
Yes. If
Well,
you
actually
made it
credit.
this far, if you made
Yeah.
it this far.
Okay, so particle kinematics. So there's two motions. One is going a straight line, which is called rectilinear, and one is curved. How do you call it?
Curvilinear.
Curvilinear, which is you go in curves no matter how small or how weird the curve is. And then it will curve the line in 2 or 3 dimensions. Okay. Okay, so position and velocity are the first two components that we're gonna get exposed to. So what's position?
It's just the distance.
Yes.
The location of
Yeah,
the
yeah,
particle.
the location of the, yes, so that, and then so that would be location x equals to 2, and if that x equals to 1, and this will be the displacement, so
Oh.
be careful with.
No,
Okay.
no judgment, guys.
To Judge Frizzle.
We are now discovering what displacements are. Yeah.
Yeah.
Stupid questions.
So displacement here, also another fact that I hope you probably know before, it's a scalar, but position is a vector.
Wait, displacement? I thought it was
No, it's a scalar because it's
I thought
the
distance is
distance.
scalar, displacement is vector. Because there's negative displacement.
Yeah, that means it's a. Oh.
How do you know
there's
that?
no, there's negative.
Distance is scalar, but displacement is vector.
Distance and displacement are the same thing.
Yeah.
Yeah, but
And they're
displacement.
both vectors. They're both
Yes,
vectors.
but like
But is position vector then?
if this is 0, this is +1, this is -1, distance is gonna be 1, but displacement is gonna be -1.
Okay. Okay, so this place. Oh, thank you for thank you for correcting that.
Okay, no, it's fine.
Exactly. But so displacement and so it's displacement that's also different from position because
Yeah,
position
yeah.
we're naming.
Yeah, position and displacement is
Yes,
probably the same.
yes. So velocity.
You derive it.
You derive it from delta x over delta t, and yeah, this is average velocity. For instant velocity, which we probably won't need here, is dx over dt. Actually, we probably will need here.
Yeah,
We don't need the average velocity. And velocity can be negative or positive. And then we jump into acceleration, which is I'm just gonna name it A. Which is gonna be the instant, is gonna be the derivative of displacement over time. Oh, sorry, it's gonna be the derivative of velocity.
Which is also the second
Yes.
derivative of the position.
And another important thing is when velocity and acceleration same direction. So when they're both positive or when they're both negative, speed up.
When they're different?
When
They
they're
slow down.
different.
Oh, because they're going in
Slow
different
down.
direction.
Yeah.
Yes.
Hell yeah.
I think I get it now.
Okay, so for constant acceleration, so for dynamics problems, if the question tells us it's constant acceleration for rectilinear motion, then we can use the kinematic equations, which is here.
They're on the formula sheet.
Yeah, they're on the formula sheet. We don't have to
Check it. Yeah.
memorize them, but you can also derive them. It's okay.
Yeah.
Yeah.
Sorry,
Sorry. Professor, she said you should understand where it was from.
So
But
that you have a very
the concept
good
for
concept,
understanding.
so you can apply it in real world.
Yes.
We took the time to derive all these by ourselves off camera. But
Yes. So
Yeah.
now we're just gonna
Yeah.
Move
Move
on.
on.
And this is for constant velocity, for constant acceleration only. So that's the only thing you do. Okay, so relative motion is a really important concept. So if I have a boat and a dead person right here,
Is that
Us.
us?
us,
Us, yes.
okay, yeah. So this is I mean, no. So okay. So if I name this A, name this B. So what's the boat's position respect to the dead student?
It would just be the position of B minus the position of A.
Yes, so we write it as B
With
as
respect
dash
to-
A, yeah.
yeah.
So that's position B with respect to A, and then RB minus RA. And then for velocity and acceleration, it's the same thing. You just have to read the question carefully to see which is respect to what.
That person isn't a good example because VA is just gonna be 0.
Yeah,
Well,
so
let's say
it's
that
a
let's say
simple
they're
problem.
both in a body of water.
Ooh.
Oh, so the body is moving.
Yeah.
And you also have to consider the velocity of the water too.
Yeah.
In that
Yeah.
scenario. Adding complex layers to the problem.
Yes.
This is what the class is preparing us for.
Yes.
Yes. So the example. Wait, sorry. 1 second. Yes. So and then we saw those questions on the homework. For the basic idea is just knowing when to, well, okay, so how I do those kind of problems, I will list a timeline. So for example, when t equals to 0, what happened, and then the two velocities, and when t equals to like 9 seconds, and that's how you use your kinematic equations there. Yeah, but
Like
you
looking at the conditions
yeah,
in
we
each
can look
time.
at conditions.
Yeah, but with these equations, when you're using like constant acceleration, the acceleration is gonna be same for all of it, right?
Mhm.
Even though it's 0 or 9.
Yeah, because it's constant.
All right,
Mhm.
that makes sense.
Yeah.
Perfect.
Okay, let's go to dependent motion. So another important concept is dependent motion. What is about dependent? Wait, this one? Oh, that's right. Dependent motion. So for a question like that, we'll probably get something with Foley system. Okay, so let's do one together. So if the question has, this is a polar, and hanging on to here, another pulley. I should have taken a picture. But it's okay. And then this connects to a block. That's a dependent motion.
Oh.
Why are you laughing? Do you like this question?
I like it.
Okay.
Is
So
it because the block's motion depends on the other block?
yes.
Wow.
Oh.
Okay.
Oh, don't we also need to constrain something? The string length. The string length gets constrained here.
Yes.
Because it's
You're
staying
very good at
constant.
answering your own questions.
I'm thinking out loud.
Yes,
and it's
yes,
working.
that's a really good point. It is, we have to constrain, that's how we solve the problem. Thank you
Oh.
for correcting that.
Hmm.
And then this will be our YB, because this will be block B and block A. So I'm just naming the distance, and that's how we supposed to find the dimension. So here, I define x, well, this is just x and y as we know.
Mm.
And then if we want to start this problem, then we have to find, well, so the cable lengths are constant, which is Claire just pointed out. If
Thank you,
that
Claire.
equals to constant, then we can do some derivative here.
L is also constant.
Yeah.
L doesn't change,
Yeah.
but since the blocks are moving, XA and YB change.
So my XA
Oh.
plus 3YB. Can someone answer why is 3YB right here?
Because there's two strings connected. There's three YBs.
So
Yeah.
Wait,
one,
what?
two,
It's three.
that's right. It depends on how many.
Uh,
Yeah. So 3YB
Plus 2L.
plus 2L. Why is there 2L?
yes, there's two L.
Yeah, so A equals to a constant. Because A equals to a constant C.
Sure.
And then let's derive this equation. So if we take the derivative with respect to time, then we have VA plus 3VB.
Three YB. Oh yeah, no. Plus 0 because 2L is a constant. So when you derive a constant, it's 0.
Yeah.
That makes
And then
sense.
this constant turns into 0 too.
Uh,
And then for VA, we know the acceleration. So we know it's 6 minutes per second plus 3
Meters.
meters per second equals to 0. So my VB equals to negative 2
Woo!
per second.
all right, guys. So we're now on lecture 18. And in this lecture, we're going to be focusing on curvilinear motion. So, Kelly, you mentioned about like, right? Why is it rectilinear motion? So now this is the curvilinear motion, which is the curvier um, siblings, I guess. So, curvilinear, so basically we have like a particle that's, all right, so basically, one thing that I want to mention is that with kinematics, we only work with particle, right? We don't work with any rigid body. Or yeah, I mean it makes sense. It won't be rigid then. So yeah, so we have a particle that's moving along this curve, and that's basically what curvilinear motion is. So first we have positions. So let's say the center is here. So we're gonna have R. And the displacement or the position is going to be the distance r, the change in r here. Oh, yep. And then we have velocity, which is we have v average, which is going to be change in r over change in t. And then we're going to have instantaneous velocity, which is just dr dt. All right. And then velocity is always tangent to the path of motion. So let's say the particle is here, the velocity is going to be tangent to it, which is over there. So for acceleration, we have average acceleration, which is just going to be change in v over change in t. And then we have instantaneous acceleration, which is going to be dv dt. And that's about it for acceleration. So for all right. So one thing I want to show you guys is the rectangular components, curvilinear motions for rectangular components. So it's basically breaking down the position, velocity, and acceleration in its I, J, and K components. So yeah. And then for accelerations, we have two types of acceleration, one tangential acceleration, and the other one is normal or centripetal acceleration. So normal acceleration, we get it by normal formula, which is just dv dt.
That's tangential acceleration.
Oh, sorry, yeah, tangential acceleration. I'm sorry about that. And then for the normal acceleration or centripetal acceleration, we have a equals to v squared over r. And then the total or the magnitude of the acceleration is going to be square root of normal acceleration plus square root of tangential acceleration, and then square of normal and square of tangential, and then you square root it to get acceleration.
And the normal acceleration is always pointed towards the center of the curve.
Yeah.
Like the center.
Inwards, yeah.
Inwards, yes.
Yeah, that's about it for this lecture 18. So moving on to lecture 19.
So for lecture 19, okay, so for lecture 19, it's just after what Muhammad said, we have a basic understanding of the tangential acceleration and the linear acceleration. So the polar coordinate is introduced here. It's a really evil coordinate that we have to show here. We have theta here and then r here. If my particle is going in this direction, we want to analyze this point. So we do the perpendicular to the line as the theta. We name it, well, to clarify. It's u theta here, but when we write it in notation, we do e theta and er. And this will be the UR component. That's the important part. V equals to R, the derivative of R, UR, which is this line right here, plus R C UR over T. And then, well, therefore, we can conclude that V actually equals to U. Well, R first derivative of R UR plus R theta, the first derivative of theta, and then U theta. So U theta is here, and the first derivative of theta, it depends on the function that they provided us. So they could provide us a function like this, so it will equal to 40. And they could provide us function like 9, and our theta will be 0, which result this the whole thing to be 0, but that's only when
Theta is a constant.
yeah, theta is a constant. And the magnitude of V equals to this is memorization. Oh yeah, and then also remember when CUR equals to 1 d theta du. Oh, sorry. D theta u theta. Based on just based on this graph. And then adding on to that, since we can conclude what V is, we can also know what A is, because A is derivative of V. And that is our A equals to the second derivative of R minus R theta, the first derivative of theta squared. UR plus R second derivative of theta plus 2R. So this means it's in the E theta direction. This means in the R, well, ER direction. So that's when they define a new coordinates and then they plug it back in here. And then the magnitude of A is equal to R. Okay. Yeah. I don't think we should go through all the equations. Yeah, I don't think. And then, okay, for the example, a really important thing that I noticed is just if we have something like if it's moving in this direction, and then our axis, this is x, this is y. But our particle moves in a half of a circle, the curve. Therefore, we have to define a new coordinate system for it, because my UR is gonna be going straight from like
Okay.
so that's my UR. And then my U theta is gonna be the
Normal to.
yeah, normal to the line. Normal to the this motion that they're, so it's gonna be my U theta.
Tangent to it?
Yeah.
So we're tilting
curve.
our
Tangent to the
our
coordinate system
system.
to this
Okay.
way. So our new coordinate system becomes u theta, ur, and then we do a e theta, er. But we have to convert it back to this x and y. So therefore we have a theta that we solve for, and then we convert it to this direction. It's like how we decomposited the force. And that will equal to the normal coordinates that we're finding. So
Yeah.
yeah, that's it. And then
So for kinetics. So for kinetics, unlike like 2D particles, just let's say here we have a box. We have weight, normal force. Let's say it's getting pushed down by P, and then there's friction. We would state it as an equilibrium statement, but instead now what we have to involve the mass and acceleration. But instead of having mass and acceleration a part of the whole FBD, a better way to go around it would be to have on the left-hand side our FBD that we would normally draw for a statics problem, but instead we are now also including a portion of for the mass and acceleration part of the for the second law, for Newton's second law. That would be m x, and that's like the general idea of it. And then so for normal and a key thing to know would be the normal and tangential acceleration of say a problem. So for a tangential, it would be a dv over dt. And it's like, and then so for normal, it would be v squared over the radius curvature. And we derive that from the equation of 1 over what's the slope dy dx squared to the power of b over 2, the double derivative of dy dx of dx squared. And that's how we plug that in to find the normal acceleration.
Cool.
And that's about it for lecture 19.
Wow, you simplify that so much. Thank you. Thank you.
Okay, we're on the last lecture now. Yay! Okay, last lecture is particle kinetics. So we've been kind of discussing what exactly kinetics is. Christian just gave a brief intro, but now we're gonna involve forces. So kind of similar to how we solve our particle systems, we are going to use F equals MA. So we're no longer in static equilibrium, as we've mentioned before. And the thing we want to introduce now are kinetic diagrams. We kind of just went over it, but for example, sorry. Okay. For example, we have a can here, and it is rotating.
Mm-hmm.
And we have some sort of theta value.
Mm-hmm.
And we're given R equals, let's just say they give us this equation.
Yep.
We can also form a free body diagram of the can, which will be helpful. So we know that there's a normal force and a weight, as always, going down. And there's also a That's all the forces actually.
Wow.
And we can also draw a kinetic diagram. So this is what's going to represent. So, sorry, we have a radial component and a transverse component here because our theta is changing with respect to time.
Mm.
So we can kind of model this. We are going to have an acceleration, a radial component for the acceleration and a transverse component for the acceleration. We need these in order to solve for the forces. So let's stay a little consistent here with our kinetic diagram.
Yep.
Yes, and we also have a, what is this? Like,
Wait, this is the FVD for this one?
yeah,
Yeah, I think what he's saying is just
That's the
the
normal
normal force,
translated.
yeah.
Translated to there to create. Oh,
So this is
again,
normal, this is odd. And then I think that's like the normal to the surface.
yeah.
Yeah.
yeah, that would be a component. That would be the component.
Okay. So there's also a normal force. Basically, the general approach to solving this is we want to create such equations following this format. We had defined our coordinate system as this, so similarly to when we have like X and Y, we could kind of just go similarly to that. And we also have our R equation here. And we have we can also solve for theta dot by using equations. Okay, sorry. Basically, when we are getting R with the change in R with respect to time, we can derive this. And we can derive it twice to get R dot dot. And then we can also find, we also know the equations for this and the equations for this. So yeah, and then when we set up our equations to solve, I already mentioned here, but these are the general formulas. So we would want to use, from this free body diagram, we know that in the R direction,
Mhm.
we have n cosine 30 because there's an angle of 30 there.
Yeah.
Minus the weight times sine 30
Mhm.
equals the weight, or sorry, the mass times the acceleration above. And now for the theta direction,
Oh,
we have, because we already defined our coordinates up
Yeah,
here, so we're
yeah,
staying
yeah.
consistent.
We are
Minus weight
consistent.
cosine, yep, stay consistent always, equals mass times acceleration, yeah. So honestly,
So this is
it's,
basically F equals to MA.
yeah, it's
Yeah.
just F equals MA, we're kind of, we have to understand though the directions of our transverse and radial components and
Mhm.
know that when we are changing theta with respect to time,
Mhm.
we will have the polar coordinates, so like
Yeah,
the
no,
theta and
I
R,
agree,
yeah.
I agree.
But F equals MA and define a new coordinate system.
And staying
Stay
consistent.
consistent. That was it for our review.
Thank you.
Thank you. Good luck on your exam. Wait, I don't know if anyone's watching this.
Good luck for your finals.
Oh, wait, I should say it first. How do I, wait, just.